Dr. Sergey Belyi from Troy University, and he will give talk on the Weyl Titchmarsh functions and Schrodinger L systems. Please, your time, Sergey.
Okay. You know what? Let me turn my camera off for better transmission. Okay. So first of all, thank you for letting me give a talk at the seminar. Huai is doing a wonderful job organizing the seminar. It's been successful for previous semester and this semester as well. My talk is, well, on a topic which is pretty much an intersection of several topics in math. That would be system theory, operator theory, mathematical physics, and a little bit of complex analysis. But that's why I'll try not to go deep in any of those, but give a general impression of what's going on. And if you guys have questions, you're welcome to ask me afterwards, where we can go slightly deeper. Otherwise, I wouldn't really fit the time. So first, some background information, definition, and symbolism and whatnot. We will deal here with what is usually called L system. So originally, an L system is considered as a pair of two equations, the one you see on the screen right now. So there are two Hilbert spaces, E and H, and an unbounded, this is super important, unbounded operator in H. This L system is an analog of what sometimes is called operator colligation or operator nodes. They appeared in circuits and basic physics theory somewhere in the middle of last century. So my scientific grandfather, Lifshitz, he was working with those, and he put forward an idea of generalizing the notion of L system to the case of unbounded operator. If operator T is bounded, this system describes an electric circuit of some kind. If it becomes unbounded, there are many problems associated with that, in particular satisfying this condition for imaginary part of operator T, because for the case of unbounded operators, it's not even easy to define the imaginary part, since the domain of adjoint could be different from the domain of original operator. Anyhow, the better way to think about the system, an L system that is as if you consider it a rectangular array, which has three operators, A, K, and J, and two spaces. On the left, you see a triplet of rigged Hilbert space. On the right, you see what's called input-output space. That's where signals would come from. So it's safe to think about the system as a box with input channels and output channels. And A, with the bold back right here, is called the state space operator. This is so-called star extension of this unbounded operator T. To give a short explanation, unbounded operators are really unpleasant to work with. And in order to work with them meaningfully, it has been created a notion of star extension. So operator bold A with the bold back is a star extension, and it's a bounded operator as acting from H plus to H minus in the rigged Hilbert space. There is a condition connecting imaginary part of A with the channel operator K that is responsible for bringing input signal into space H minus. And J is the so-called signature operator describing pretty much the environment where all this is going on. It's both self-adjoint and unitary. The entire theory of L systems is given in our book, Conservative Realization of Herglotz-Nevanlinna Functions, published in 2011 in Springer, Berkhäuser, Weyland. So we will be interested into three elements of an L system. T is a main operator, that's unbounded operator we talked about. A dot is a symmetric operator, the largest common Hermitian part of T and T star. And of course, A with a bold back I already talked about, the star extension, and A hot is a quasi-kernel. The proper name is quasi-kernel of real part of A. Essentially, it's a self-adjoint extension of A dot, which is a part of a real part of bold A that stays within the main Hilbert space. The reason they is highlighted in red is because that triplet A dot, T, and A hat define an L system uniquely. In other words, if I provide A dot, T, and A hat an appropriate Hilbert space, I'm fixing on one particular L system. There are two objects associated with an L system coming from the system theory. The first one is a transfer function, a W. So if you remember on the first slide, there were two equations forming the system. So if you solve one for the state space vector X and stick it into the other one with the substitution, you will have a mapping under favorable conditions, of course, that connects input and output. So if you think about the system as a black box, so this operator function W takes input directly into output. And even richer object is the so-called impedance function of an L system, which is the linear fractional transformation of W. Or it could be written directly using the elements of the original L system. So typically, there are two types of problems coming from a system theory associated with L system. So there is a direct problem, which goes like this. You are given an L system, and we need to figure out what the transfer function of the system is and classify the impedance function. In a way, impedance functions are a little bit better objects than transfer functions themselves because they are holomorphic and they possess certain property, but we'll talk about it later. So this is direct problem. We have an L system and you're trying to see what transfer and impedance functions are. And of course, there is an inverse problem where you are given a function of a certain function class, and we need to construct an L system such that this function serves as an impedance function to the system. So basically, you're building a model of a system that has impedance equal to the function you're starting with. And both problems were solved in the class of so-called Herglotz-Nevanlinna. Sometimes people call them Nevanlinna functions. Sometimes people call them R functions. There are different names. I guess in our book, we start with Herglotz-Nevanlinna name to give proper credit to everybody. So we are in operator valued case, of course, we are talking about an operator function in a finite dimensional Hilbert space E if three things happen. V of Z is holomorphic in the upper half plane. Imaginary part in the upper half plane is non-negative, and there is a symmetry property. Symmetry property that you can, use to reflect upper half plane to lower half plane for this function. So the reason I'm mentioning Herglotz-Nevanlinna functions here is because the problem, like both problems, direct inverse, was solved in this class. And the solution pretty much lies and is laid out in terms of integral representation, because all Herglotz-Nevanlinna functions are admitting the integral representation that you see on the screen right now, formula 3. And certain conditions could be applied on the elements of this integral representation to select the functions that are realizable, that fit the class which is relevant for solving direct and inverse problem. So the name of this class is NR, and the conditions that needs to be met is, of course, V of Z has to be Herglotz-Nevanlinna function, and this integral representation linear term should be 0, and the measure in integral representations should be such that the constant term in integral representation applied to vector x would behave like that. So these three conditions let us solve the directed inverse problems. So a direct problem would sound like this. Let's take an L system of the form 1, then the operator function V theta of Z, that is impedance function, belongs to the class NR. And backwards, an operator valued function belonging to class NR admits a realization by an L system of the form 1, and you can even say more, you can actually realize it with J equals 1, so it's a so-called scattering system. This is an old result. It even predates my PhD dissertation, 1992. Sometimes people say that if you take the intersection of all your papers, you'll get your PhD dissertation. It's not exactly true in my case. So this paper came out in Soviet Mathematics Doklad in 92. I was still in grad school. The paper was my advisor. So for our purposes here in this talk, we'll use a lighter version of an L system. The input-output Hilbert space E will be simply taken to be set of all complex numbers C. Signature operator J is taken to be 1, and operator T is dissipative, and operator A dot has efficiency indices 1, 1. So it is a light version of a definition of an L system, which is sufficient for our purposes for what's going to happen next. And the rest just follows. A with a bold back is still star extension of this dissipative T, and imaginary A is K star. So since J is simply number 1, condition simplifies. Moreover, both transfer and impedance functions are scalar functions now, which obviously makes life a lot easier for this particular case. All right, so this was all the background we needed on L systems. Now let's talk a little bit about L systems with Schrodinger operator. Those are going to be the ones that fit the definition of one-dimensional input-output system from a previous slide, L system Y. And usually they're used as a very nice model for system building like that. So a little bit of background on how to create an L system using Schrodinger operator. To begin with, let's take Hilbert space L2 on a half axis, and second order Sturm-Liouville operator here, or differential expression minus y double prime plus qxy. The potential q here is considered locally summable, real locally summable functions. So we'll consider operator E dot a symmetric operator based on this differential expression with boundary conditions zeros on the right end, and efficiency indices 1, 1. And our main operator, TH, it's what's called Schrodinger operator, named after Schrodinger because that's where two theories collide, like Schrodinger equation and Sturm-Liouville equation. H is essentially non-real. So imaginary part of H should be positive. So TH here plays the role of the main operator in the system we will build. All right. There is another object which is super important in the Sturm-Liouville and Schrodinger theory like that. If we consider the same differential expression from previous slide, that L negative y double prime plus qxy, and solve two Cauchy problems with these initial conditions 0, 1 and negative 1, 0, then there exists a function named m infinity introduced by Weyl such that, yeah, that's Weyl, such that phi of x, the combination of solution of the second system and the first system, belongs to L2. Belongs to L2. And so Weyl function, or as some people call it, Weyl Titchmarsh function, plays a super important role in Schrodinger operator theory, and there are numerous papers written on Weyl Titchmarsh function and its generalization here and there. So it's present in lots of results for this theory. What is interesting, though, from our point of view, is that even though m infinity is not Herglotz-Nevanlinna function, but its negative is, and its reciprocal is. And we will try to use this fact in what follows. So another result that is super relevant to what we're about to do is this. It has been proven that all star extensions, and star extensions is what we need to compose an L system, of the Schrodinger operator TH, of the form 6 from slides below, can be represented in the form 7. So if you notice, there are two parameters, mu and h. Mu is a real number, and h is the boundary condition for TH main operator, so that all A with bold backs are written in this form. But literally, you can take fixed operator TH and run your mu all over the extended real line, negative infinity and positive infinity included, and every time we will be getting a star extension. Moreover, all star extensions of Schrodinger operator are described like that. The result was obtained by Yuri and Edward in 2004, and here is a reference. So one can create an L system with a Schrodinger operator because all components are known and that are there. So simply you create a system theta with a star extension A mu h from a previous slide. You create triplet of a Hilbert, rigged Hilbert space right here based on the central space L2 on semi-axis. These are like some kind of Sobolev structures here. And choose channel operator K as simply acting from C into H minus by multiplication by the complex number. So what K does, it takes a complex number and multiply it by a channel vector G, which is written like this, also in terms of mu and h. As a result, you're getting a family of L systems that are parameterized by two numbers, mu and h. So literally, you take two numbers, plug them in here, and you're getting a ready system based on a given Schrodinger differential expression. Moreover, it has been calculated the value of a transfer function. And again, you may see that it's the answer is given in terms of mu, h, and m infinity. Herman-Weyl's function, m infinity, and impedance function. In other words, both elements needed to solve direct and inverse problems are also written out, and they are written out in terms of mu, h, and m infinity. So very convenient model for L system theory. Okay, and that's where we begin the new stuff. So what happens next? Natural question arises. We know that function m infinity is not nonlinear, but negative m infinity is, and so is the reciprocal. So negative m infinity and 1 over m infinity are both Nevanlinna function. Question, are they realizable? Do they fall into the class of an R that can be realized? So one venue to take is to start working with their integral representations, but there is a simpler solution. One can take a shortcut and try to build a particular Schrodinger system that would realize negative m infinity and 1 over m infinity directly. After all, in order to create a realizing system, you just need to present an L system. Okay, and this is what we are going to do. So to be specific, we are trying to come up with a Schrodinger L system such that it has values of mu and h. Remember, two parameters we talked about, so that it realizes one of these two guys. So literally the question afterwards is, what's the value of h and what's the value of mu? And of course, if we operate in certain settings, we already know m infinity. M infinity doesn't come from blue sky. It is associated with some kind of differential expression, Schrodinger differential expression, and there is a Hilbert space already fixed ahead of time, and there are plenty of results setting up one-to-one correspondence, like Borg theorem, for example, between the potential and m function. Okay, so here's the answer to the question. Apparently, nobody tried to do this, even though those objects have been around for quite a long time. So it turns out that in order to realize a Herglotz-Nevanlinna function negative m infinity, one needs to take the value of mu equals 0 and h equal I. So these two numbers produce a system with 0 and I such that negative m infinity is the impedance function for this one. And it works both ways, so it's a criterion. So conversely, if you take a Schrodinger system of the form described before, and those two parameters are the ones defining it, then the impedance function matches negative m infinity. So parameters are 0 and I, the ones that do the job. Moreover, this system can actually be written explicitly. So for letting mu be 0 and h be I, we'll get in the following nice version of star extension, as you can see in Formula 11. Operator k is also very specific. We know that delta function prime here serves as a channel vector, and just multiply it by number c, you'll get it. What is interesting is that when one calculates the real part of state space operator here, it's quasi-kernel, and quasi-kernel is again the part of the operator that doesn't stick out in the space of linear functional, so you need to cut it. And so it happens to be that quasi-kernel of this is a well-known Dirichlet boundary problem. Dirichlet boundary problem, which is used a lot these days for groups of people who study boundary triplets. So Schrodinger operator with Dirichlet boundary problem serves as a quasi-kernel for this system. And remember why this should excite us, because three things define the system uniquely: a dot, a hat, and th. Th is given because h is given, it's I, it's ti. A dot is pretty much given for as soon as, you know, operator L set. But the third ingredient, a hat, self-adjoint extension, happens to be Dirichlet boundary problem, and that fixes the system in place. Moreover, you explicitly write impedance and transfer function. Of course, impedance is negative M infinity. That's how we built it in the first place. But transfer function is also explicitly written. Now we'll repeat the same for the other Herglotz-Nevanlinna function, the reciprocal one, 1 over M infinity. And so this time the values of the parameter should be infinity and I. If you notice, H did not change. The central operator or main operator of the system is still Ti, but the value of mu is infinity. And that does the trick. The system with these two parameters realizes 1 over infinity. And backwards, of course, any system with two parameters like that, infinity and h, have its impedance equal 1 over infinity. As before, we're going to specifically write the system up. So L system infinity I is given by the array 14, where the main or the state space operator A infinity I is this. K infinity I is multiplication by the channel vector delta function at point L. Real part of A infinity I is this, and quasi-kernel again hits the famous boundary value problem. It's a Schrodinger operator with Neumann boundary conditions. So this is a Neumann boundary condition, and that's what defines the system realizing 1 over M infinity. So very interesting. So those two functions happen to be special. The first one, negative M infinity, is realized with the help of Dirichlet boundary condition, and the second one is realized with the help of self-adjoint extension with Neumann boundary condition. And again, you see impedance and you see transfer function written out here. Then we decide to take the same problem on a little bit next level and consider it sort of a generalization of M infinity. See, terminology here is kind of different from different group of people who work with that. And let's call them Weyl function, not Weyl Titchmarsh, but Weyl function here. So parameter alpha is thrown in. And instead of considering two Cauchy problems as a definition of M infinity with 0, 1, negative 1, 0, you do more general result. You can find it in a Titchmarsh book. You can find them in the work of Levitan and others, Nymark. So they call them Weyl function, and there is a parameter alpha here, which pretty much works the same way it worked for M infinity. So M alpha is a function such that the combination of solutions of two alpha dependent Cauchy problem belongs to space L2. M infinity is a special case of M alpha. Moreover, M alpha and M infinity are connected with a linear fractional transformation found in the works of Titchmarsh and book of Levitan. It's a known result. Moreover, M alpha becomes M infinity if alpha is pi. So what we do is, for our purposes, since we don't work with functions M directly, they're not Nevanlinna, they're kind of anti-Nevanlinna. We'll throw minus up front and modify this linear fractional transformation. And so now on the left of the formula 18, you see a Herglotz-Nevanlinna function minus M alpha z and its connection to a Herglotz-Nevanlinna function 1 over M infinity. Again, it's a little bit modified LFT 17, but now it relates to Nevanlinna functions. Okay, then the results will follow. We still working on realization of negative M alpha. So if M alpha is the function described before, then the Herglotz-Nevanlinna function negative M alpha can be realized as a Schrodinger L system of the form A with these two parameters. Mu has to be chosen to be tangent alpha, and H is still I. And backwards, of course, if there is a Schrodinger L system of the form such that its impedance matches negative M alpha, then the defining values, defining parameters should be tangent alpha and I. Moreover, we can again explicitly write out the system. So there is a typo here. It should be tangent alpha. Obviously, I copied and pasted from previous slides. So mu is tangent alpha is right here, and still I. Star extension, and we're talking about entire family of systems and star extension because everything now is alpha dependent. So the family of star extensions is written like this. You see tangent alpha appearing here and there. There's a channel operator with channel vector written like that, also alpha dependent. There is alpha dependence in the real part, barely fits the screen. There is a quasi-kernel right here. No more pictures and fancy names anymore because it's just general description of all alpha quasi-kernels. And finally, the results for impedance and transfer. So this is impedance, that's what we are building it to be. And that's a transfer function, input-output mapping. And of course, the picture wouldn't be complete if the same problem was not solved for the reciprocal 1 over M alpha. 1 over M alpha is also Herglotz-Nevanlinna function, and the question is what values to take. So mu is going to be negative cotangent, while H is still I. And structural theorem as before, it's a criteria. It's forward and backward. So Schrodinger system of the form 8 with the impedance matching 1 over M alpha must have parameters negative cotangent alpha and I. And again, explicit description of the system. So you'll see negative cotangent appearing here. That's a star extension, that's a channel operator, and so on. Quasi-kernel, and to final result that finalize it. All right, now all these leads to what we call the uniqueness theorem, which tell us that pretty much there is exhaustion property. So if we take a Schrodinger system with second parameter I, and mu could be anything, any real number infinity is included. So then there is a unique value of alpha such that the impedance function of such a system matches negative M alpha. So there is one-to-one correspondence between all angles from 0 to pi, 0 is excluded, and all family and family of L system with impedances equal to negative M alpha, which is pretty neat. But of course, it's based on the property of tangent being one-to-one and onto. Okay, and that's all the theoretical part. Of course, it's nice to look at examples of these. What we do, we take another textbook example. So Schrodinger operator with a Bessel potential. So what you see here is a parameter nu that creates a Bessel potential. Nu is a positive number. Hilbert space is taken from 1 to infinity. Minimal symmetric operator is right here. A dot with 0, 0 for function and derivative on the left end. Its deficiency indices 1, 1. And the operator th, same differential expression. Y prime of 1 is h while 1. So this will serve us as a base for two examples that follow. Example 1, if you take nu equals 1/2. So you can go in one of the books on Sturm Weyl theory or differential operator, let's say book of Neumann, and get that M infinity in this case is negative I times square root of z. It's a particular function. This is well known result. If nu equals 1/2, that would totally kill that expression in the Schrodinger's Bessel potential, and our operator is simply second derivative with a minus sign in front. So a dot, the symmetric operator, is a very simple object. Negative y double prime, y1 equals y prime 1 equals 0. The main operator we're going to write for h equal I, because it appears to be a special value that is common for all the families of all the L systems realizing Weyl group of functions. And so we put I in here. Okay, and now we can actually go ahead and use our theory and construct L systems realizing negative M infinity and 1 over M infinity for this particular case. And we are doing so. So we just follow the rule, put numbers in, crunch these expressions, and that's the formula we obtain for star extension A. That's a formula for channel vector and corresponding channel operator K. Here is our impedance, which is just negative of M infinity. Negative. Oops. And of course, transfer function right here. Very simple objects, calculatable. Now we can do the same for 1 over M infinity, which in this case, it happens to be I divided by the square root of z. Again, I'm following the theorem, applying all the formulas here. And here is my theta infinity I with state space operator A infinity I written like this. Channel vector delta function of x at -1, channel operator, and two objects, two functions associated with this. The actual impedance, the one we're realizing, and transfer. This was example 1. Example 2, we take nu in the Bessel potential to be 3/2. The formulas become bulkier, but the result is a bit richer. And this time, we will try to realize M alphas, not infinities, but M alphas. So when nu equals 3/2, you go to the book on differential operator of some kind and fish out the value for M infinity. This is 1 minus I squared. z divided by square root of z plus I. By direct substitution, m infinity at 0 from the left is 1. So minimal symmetric operator becomes this. So now there is a potential here, 2x squared. TH with h equals I will be that. And from this point on, we can start realizing minus m alphas. And here we go. First of all, it would be nice to see what m alphas are. We're going to shoot straight for negative m alpha because these are Herglotz-Nevanlinna group. And simple calculation, well, maybe not so simple, but still calculation that requires the formula, and let us use this expression for negative m alpha z. Okay. Then the realizing system, well, tangent alpha as mu will look like this. That's its formal description, but this is a specific description for any angle alpha with this potential. That's operator, channel operator k with 2 subscripts, and that's a vector, channel vector g that defines. Impedance is this. Well, that's what we're realizing. And here is the formula for the transfer function. It has an interesting connection to m infinity right here. So you have a unimodular factor up front, negative e to the 2 alpha, but describes them all. Okay. And that's basically all that I wanted to tell you. The bibliography, all the L system descriptions and theory and everything is in our book, Conservative Realization of Herglotz-Nevanlinna function. All the new material on the realization of Weyl and Weyl Titchmarsh functions are in our fresh paper this year in complex analysis and operator theory. It's already an archive. If you're interested, I can give you a link, or it is on my website. So this is it, and thank you.
Yeah, thank you very much, Sergey. Do you have any questions for our speaker? I have a small question, Sergey, regarding the integral representation.
Yes.
Yeah, it seems like very similar to the case of operator-Morton functions. As you know, the theory of operator-Morton functions comes from like Nevanlinna functions.
Yeah.
So I feel like, yeah, it's very similar. Yeah, that one.
Yeah, yeah.
So,
yeah.
but in this case, you consider operators like Q is a operator, QRL.
Yes, it's a bounded operator in a finite dimensional Hilbert space. I mean, of course, here in my talk, I work with scalar objects only. So I guess, the first place you could see the useful work with this integral representation is a book by Atkinson, and there is an addendum by Katz and Crane. So you can only find it in Russian edition of the book, unfortunately. I don't know why, but it's that's the best source of all classes of functions that come out of this integral representation. It's very rich, even though it's done in a scalar case, but then there are generalizations. I mean, with typical techniques, you can raise it to matrix functions and bounded operators. But all the groups, like the Still-TS group, inverse Still-TS group, and others, they all can be found in this addendum to Atkinson's book. So yeah, maybe if you're talking monotone, I'm thinking that there were some works on monotone Nevanlinna functions. I'm just trying to remember whose I haven't seen in a while. But yeah, it's a very common family for many problems for certain reasons. It has to do with spectral theory, as a matter of fact.
Yeah.
of self-adjoint operators and the one close to self-adjoint.
Yeah, and the function gt in this case, that is
Yeah,
non-decreasing operator value function.
it's a measure. It's a measure.
Yes, it actually is the measure, and then the condition like the integral on R, dgt xx on e over 1 plus t squared less than is finite, right? It's some kind of finite measure.
Yes, yes. That's condition. I mean, essentially, if you take like I and minus I and plug it in, so this what would collapse into this integral. Yeah, it's a non-decreasing measure with these properties, right?
And one more, I saw in very some kind of symmetry, right? You consider some symmetry J equal to J
Yes,
star,
yeah, it's a general, yeah, that's what's called here.
Yes.
Signature operator, operator J. Yeah, it appears in the most general case of L system. So that's where it has to do with certain environment, because I told you it all grew out of a circuit system, and when you connect electrical circuits, J has a particular engineering meaning. So when the systems were defined first for bounded case and matrix case, there were systems where J is not one, could be -1, it could be 2 by 2 matrix or signature matrix. But the important part is like it has to be both self-adjoint and unitary at the same time. So it's a really neat. It's like you can think of a 2 by 2 matrix like 0I and -I0. So that's your typical signature matrix. You could pick one, for example, like identity matrix. It will certainly work. Yeah.
It just reminds me about the space of Hilbert space with indefinite metric.
Oh yes.
Generated by some symmetry. So
yes, but it's not the same. As a matter of fact, we had some papers on systems in Pontryagin spaces.
Yeah, Pontryagin space, yes.
With indefinite method, but there is a J and there is their J for square bracketed self-adjoint. Yeah, it's sort of the same object, but like the funny thing, we encountered the problem that we have to have both in the same paper. So there is that J, and we would write curly J for the other one, for the space with indefinite.
Yeah, you know, when I saw notation like H plus, A minus, and H, so it just reminded me about that. Because, you know, if you consider Pontryagin space, so
well, it's a little bit different. In Krein and Pontryagin spaces, there is like three of there is H plus, the positive definite part, there is H minus, and there is isotropic part. Well, that's not it. It's a little bit different. It's a more Sobolev structure here.
Okay.
So there is a Hilbert space H, and inside it there is a dense set H plus, which is a domain of a joint operator. I mean, when you start working with unbounded operators, all things like turn loose. And to create a triplet, I mean, you take this dA star domain of adjoint and consider a space of linear functional. This is a generalized space, H minus. So you go through all this trouble to, you know, avoid working with unbounded operators. So if your operator is unbounded, you make a larger space where it is bounded. In other words, if Muhammad doesn't come to the mountain, mountain would come to Muhammad. You know, so that's one of the principles here. So that's how rigged Hilbert spaces came around. It's entire theory. There is a book on that. There is a relation between norms and metrics, and then recalculate. But when you work with something like differentiation operator or Schrodinger, you saw those delta functions. These are Dirac functions, and these are the beasts that live in H minus. So they're linear functionals. So that's what would make H minus. You cannot really touch them. You can make apply Rees theorem, representation theorem, make an inner product with them to get a meaningful result. But it's going to be one point. It's like it's impulse. So that's what H plus and H minus here. Yeah, it's not as straightforward as indefinite metric H plus and H minus.
Okay, thank you. Okay, do you have anything else for our speaker? So if not, let's thank our speaker again for his interesting talk, and we'll see you next week.
Thank you for listening. Yes.
Thank you.
Yeah, thank you everyone for
Sergey.
being here.
Thank you, Sergey.
My pleasure.